When we design systems to solve complex problems, the default assumption is that intelligence scales with absolute freedom. We assume that if we give a system infinite time and unbounded space to explore every possibility, it will eventually generate complex, meaningful structures. But the mathematics of complex systems dictate the exact opposite. Unbounded stochastic exploration, searching randomly without strict limitations, does not build complexity. Instead, it ineffably degrades into entropic noise. The mathematical embodiment of this flawed assumption comes from mathematician Emile Borel in 1913. He proposed the infinite monkey theorem, arguing that given enough time, random keystrokes will eventually produce the complete works of Shakespeare. This is an ergodic assumption, the belief that uniform probability and infinite scale eventually yield profound structure. Anthropologist Gregory Bateson dismantled this idea using the cybernetic principle of negative explanation. Negative explanation states that intelligible structure is the result of systematically eliminated alternatives. Meaning emerges not by finding the right answer in an infinite sea of options, but by making the wrong answers impossible. This introduces a framework we can call generative limitation. It is the principle that boundaries are not passive containers restricting a system, but active mechanisms that create a system's autonomy. We can trace this exact mechanical requirement across entirely different scales of reality, from the physical formation of crystals up through biological life, human cognition, artificial intelligence, and existential consciousness. To understand how reality builds meaning, we must map exactly what a system systematically makes impossible. Classical philosophy often relied on hylomorphism, the idea that physical objects are created when a pre-existing form is imposed onto passive matter. This view treats boundaries as external molds. Philosopher Gilbert Simondon corrected this by identifying the pre-individual state. Before an entity exists, the environment is a metastable, supersaturated system charged with incompatible potentials that cannot exist simultaneously. This diagram of transductive crystallization illustrates how a seed crystal grows inside a supersaturated liquid. Its outer boundary is not a static wall. It is an active transductive geometric growth front, where each new molecular layer dictates the structure of the next. The primary metaphysical takeaway here is that the limit of a physical entity is its operation. The boundary is the engine of its creation. For a physical object like a crystal, this operation happens entirely at its exterior edge. But biological systems must internalize this physical boundary constraint to survive. This schematic of a biological cell's recursive feedback loop demonstrates how organizational closure, or autopoiesis, functions. Its boundaries selectively filters specific environmental interactions while blocking others entirely. By severely limiting which external forces are allowed to affect its internal state, the organism establishes a functional identity separate from the chaotic environment. Biological individuality is therefore not an inherent static trait. It is a continuously generated product of rigorous environmental exclusion. Moving from biological survival to human cognition, we often assume that creative thought requires the complete removal of constraints, treating imagination as a purely unrestricted process. Simondon's creativity paradox states that true output is a multiplicative function of novelty and usefulness. These variables exist in inherent tension. Extreme novelty lacks utility because it breaks too many rules, while extreme usefulness relies on established unoriginal conventions that offer no innovation. When people attempt to solve open-ended problems, they face functional fixedness. This is a cognitive hurdle where existing memory and semantic networks act as structural constraints that stifle the generation of novel ideas. The solution is creative realism, which requires the intelligent misuse of these memory constraints, rather than their complete abandonment. The mind must work against its own structure. This brain network model highlights the default mode network branching into unconstrained abstract search paths. Conversely, the executive control network acts as a reductive filter, clamping down. True creative insight demands their forced coactivation, generating value through a localized zone of high-tension structural constraint. Ultimately, psychological freedom and human innovation are biologically and structurally dependent on the rigorous application of inhibitory control. This principle of generative inhibition extends beyond subconscious creative generation, dictating the structural requirements of conscious awareness itself. This vertical scale maps the scale problem of consciousness. Human awareness is blind to microscopic neural firing and macroscopic systems, experiencing only a specific middle layer. Subjective experience requires information closure here, forming a recurrent feedback loop visually severed from surrounding noise. This information closure allows the brain to model the environment effectively by predicting and heavily constraining sensory input, preventing the mind from being overwhelmed by raw data. The constrained disorder principle, or CDP, further details this dynamic. The brain requires a very narrow, dynamic border of variability to function, balancing highly ordered states with necessary pockets of randomness. The failure modes are severe. Too much constraint yields a coma, while too little yields a seizure. An individual's conscious perspective is an isolated island of meaning, sustained entirely by the active filtering and exclusion of the vast majority of physical reality. We can apply this cybernetic logic to artificial intelligence to empirically test the ergodic fallacy we introduced earlier. A prevailing industry assumption suggests that recursive AI training on infinite stochastic data, endless unstructured text from the internet, will naturally evolve into general superintelligence. This schematic shows two diverging AI training pathways, demonstrating model collapse. The left is regulated by constraints, maintaining diversity. The right operates unconstrained, recursively training on its own synthetic output, homogenizing into a flat line representing model collapse. The loss of human-derived asymmetric constraints forces these recursive algorithms into a state of entropy maximization. Without external boundaries dictating what the model cannot do, the outputs become repetitive and meaningless. Alan Turing demonstrated that meaningful output in artificial systems requires strict algorithmic boundaries and finite computational limits. Claude Shannon built information theory to quantify these boundary constraints, proving mathematically that signal clarity depends entirely on the reduction of noise through selective filtration. We can shift from the artificial constraints of computation to the ultimate boundary placed on human cognition, existential finitude. Heidegger articulated being towards death. Mortality is the absolute boundary that breaks symmetry, forcing individuals to form an authentic self. Just as an AI model collapses into entropic noise without algorithmic limits, human meaning and individuality dissolve into the anonymous collective, without the structural constraint of mortality. This four-tier structural dependency stack tracks this architecture from physics to philosophy: physical transductive limits, biological organizational closure, mutually inhibitory cognitive networks, and informational finitude. This reveals an invariant principle. Meaning is defined strictly by what a system makes impossible. We call this generative limitation. Meaning does not, and mathematically cannot, emerge from the exhaustive accumulation of infinite possibilities. The final epistemological lesson is that boundaries are not obstacles to complexity. They are the exact architecture that prevents the universe from remaining a homogeneous entropic wasteland. To build, understand, or emulate true intelligence, we must stop asking how to maximize a system's freedom and begin asking how to engineer its constraints.